The topic today is to disaggregate the data center and conquer complexity. To discuss this very wide-ranging topic, we have assembled a panel of experts who, between them and individually, cover a lot of ground. This particular topic has gotten a lot of interest in the last few years, partly because the whole hyperscale infrastructure is becoming extremely complex and extremely convoluted, and just keeping it going is turning out to be challenging. To solve many of the problems that we encounter, disaggregating the various components is a thought that people have. It's not a new thought, but the need for it is maybe relatively newer, and some of the tools we have are also newer. So with that, let me introduce the panel. So I'm Jay Shenoy. I'm the VP of Technology at Hyve Solutions. And joining us today are Amir Michael. Amir is currently the Chief Evangelist at Lightbit Lab, but you probably may know him from his early work in the OCP community because he was one of the founders of this whole thing, being an early hardware engineer at Facebook. And he also mentors quite a few startups these days. The second person we have is Manoj Wadekar, presently at Facebook and presently working on storage, although that is one of his many talents. Previously, he has been a network architect at Intel, and at eBay, his architecture portfolio covered the gamut of storage and servers and deep learning and many other topics. Anjanaya Chagam, also known as Reddy, is a cloud storage technologist at Intel. He has worked quite a bit on Ceph, but he has worked actually on practically all the cloud storage technologies of note, and especially and most recently and most notably on NVMe over TCP. Next on the panel is Jay Menon, the chief scientist at Fungible. Jay, you may know him from GPFS and his many algorithm contributions to RAID. And at Fungible, of course, besides storage, he's also involved in security of any kind, as well as networking, of course, because Fungible is a networking company. And lastly, but not the least, we have Parantap Lahiri, who is VP of Infrastructure at eBay. His group covers networking, hardware, as well as data center operations. Parantap himself has built a number of internet network infrastructures at Microsoft, at Visa, and also at eBay. So Parantap has quite a bit of background in architecture and operations of large-scale networks in data centers. So with that, let me start this panel discussion, and I will begin with Amir. So we have a pretty interesting title, which is that complexity that needs conquering. So Amir, can you tell us about what is this complexity that needs conquering, and is there even a problem here?
Sure. I'll start off with some of the reasons of why you might want to do things like disaggregate. One of the primary ones I'll begin with is really about resource utilization. And I'll begin that with a story. Back in 2010, I was working at Facebook, leading the team of hardware engineers that did the first version of the Open Compute servers. And when we finished, after about 1.5 years, we came up with a financial number that said our servers are 28% less expensive than what we were purchasing previously. Now, at the same time, there was another team that was working on a project called HPHP. And they were building a piece of code that took PHP code, translated it to C, and then compiled it, and it ran on our web servers, which was the majority of our servers that we had at the time. That project saved 50% of utilization. So automatically, we needed half the number of servers that we needed before to run the same number of applications. Now, that's the impact of something like disaggregation that brings down utilization numbers. It has a huge impact. Now, disaggregation isn't something new. We've known it before with things like SANs. We've known it before locally on a server with things like virtualization. We've known it more recently with infrastructure called HCI, or hyperconverged infrastructure. It's the sharing of resources across applications. It has lots of impacts. For example, financial, like I talked about before, the supply chain becomes simpler. You're perhaps buying fewer types of server SKUs. You're planning capacity around commodities like DRAM and flash and CPU rather than capacity for applications. You're engineering servers that are designed to go around specific commodities, not necessarily for applications. Management like reliability or redundancy can happen at a lower level, not necessarily on the application level. And the product can perhaps ignore some of those lower level things like reliability and redundancy and really focus on the product. So it has a broad impact. As a whole, disaggregation in the past has focused around slow commodities like hard drives that inherently have a lot of latency built in. Today, the challenge that we're trying to conquer really has to do with how do you disaggregate things that are more latency sensitive, like flash, perhaps DRAM is the next step, or even CPUs where you're using these resources remotely in a shared pool as opposed to local resources only. So that's really where the challenge is that I see today.
Okay, so performance as well as addressing commodities or addressing things at a very understandable commodity level. Right?
Yep.
Okay, so the next then question is for Manoj, and Manoj, put your sort of broad hat on and sort of, can you discuss what data center disaggregation means for hyperscale in particular, because OCP is about hyperscale.
Yeah, thanks, Jay. And first of all, of course, thanks for putting this great panel together. Thank you, I appreciate that. And it's a great question. From hyperscale perspective, and Amir did talk about what his experience had been from the Facebook perspective. In general, efficiency, of course, definitely very important for hyperscale, right? I mean, the numbers are pretty large, so any capacity or performance trending shows up in the unoptimized utilization in the fleet. So disaggregation at a high level where compute and storage, if you take that as an example, can help us to scale independently for the applications. And this really was driven when has been shown to be driving much faster, because as we see, the compute and storage isn't growing at the same rate. Storage growing faster, and so putting SKUs together becomes a challenge, can lead into a lot more stranding. And at the same time, networking bandwidth is growing very nicely, so that does make a solid case for disaggregating the compute and storage. And once we do that, that does allow reduction of SKUs, which in the fleet at hyperscale level allows us to reduce any kind of double counting you have in buffering that you have to maintain, any kind of silos. So it does allow you to not only improve the capacity utilization, but many times it's also the trade-off for the performance, because many of the stranded capacity in this fleet also means that performance is not being used from those components. So it does allow you to do both together, which both of them are extremely important from hyperscale perspective. Now, the key aspect from hyperscale side is also the capacity and performance needs grow so fast and so widely that the solutions tend to be scale up from compute point of view, and then also it's going to be for storage perspective. So the disaggregated storage services that we're going to provide need to continue to scale in that scale out fashion. That's going to be the important requirement. Once you do that, the important thing that it enables is also it enables agile development for the application folks, because many of the application folks that have to think about what storage services that they need to provide for their own requirements, the moment you separate that out, they can focus on the goal of the application and move the responsibility for the storage to the storage services that are being built into the storage, disaggregated storage. So this does, of course, this does increase the responsibility of the storage service also now, because you have to make sure that this storage is going to be available, reliable based on the application needs, and there could be different types of applications that they need it. You may want to have the availability across multiple domains, whether it's a data center or region or zones. So all that functionality needs to be supported when you're catering for the hyperscale needs into the disaggregated storage. And these services, another important thing to see from hyperscale perspective, the scale is so high and the pace expected is so high that you really cannot go back, you cannot reproduce any issues that are happening in the fleet. You have to be continuously monitoring them. You have to continuously allow the maintenance of the system. And that's important for the maintenance of the services, and also the ease of access, how the applications can use the services. So bottom line I can say is that disaggregated storage is important, but it needs to be thought through as storage services that applications will consume dynamically in the fleet as compared to that being a build time option. So that I think is a nuance but extremely important difference from hyperscale perspective, in my opinion.
So, Reddy, the next question is for you. Both Manoj and Amir talked about storage. Manoj ended directly with storage performance, and Amir kind of alluded to it when he was talking about flash, and maybe the latency of the network would not be would be a challenge, even though bandwidth may be fine. So the question is, for all of this to work, can network storage perform to the expectations that we have and to the expectations that we are used to with local SSDs right now? Can you take a whack at that question?
Sure, yeah. So Amir actually talked about few things, right? So the storage disaggregation has been there for quite some time. So if you look at, some of the early incarnations of the network storage, so ATA over Ethernet, for example, very early on, you might have come across iSCSI, essentially taking the SCSI protocol, transporting it over the network, be able to actually attach a drive that's actually shared by the target, has been there for quite some time. Some instantiations of the network protocols like iSCSI or Ethernet RDMA, fiber channel over Ethernet, they have been quite popular in the scale-up appliance model, right? So most of the storage vendors out there have been exposing the virtual storage capacity over the network using one of these protocols for quite some time. Whether we call this as an initiator on the client side and the target being the storage appliance, but predominantly early incarnation of the network attached storage has been primarily used for niche use cases, mostly databases and some high-end applications, and deployed in a very, very well orchestrated, low latency fiber channel or Ethernet type of infrastructure, right? Now, over the course of time, what happened was you take the scale-up model, take advantage of some of the standard high volume server type of deployments out there. And then if you can actually pool the storage that's actually part of each one of these servers, standard high volume servers, and if you can actually create a mechanism to abstract the location aspect, and then create some logical notion on top of that, you can essentially get to a scale out storage. Now, this concept is well proven by hyperscalers. And over the past 5 years or so, you have actually seen quite a bit of scale out storage type of implementations, even in the mainstream. And whether it is the private cloud, enterprise, most of those implementations have been predominantly on the scale out. Now, scale out also brings very interesting properties, right? So you can actually distribute your content, among pool of servers, which could be within a region, which could be in multiple regions. You can actually get the geo resiliency and all that stuff. So there is a distributed resiliency aspect also that you get out of the scale out storage. And then you also have a mechanism to extend the block semantics to object and file. Now, bunch of these architecture patterns have been adopted for higher level services too. If you look at some of the database as a service pattern that you normally come across with the, tier one, infrastructure as a service type of, services, you do see that kind of higher level semantics as well. So the maturity is there from scale up to scale out to, somewhat higher order, services. Now the challenge, like Amir talked about in some shape or form, Manoj also mentioned that in his previous discussion. How do we take advantage of this architecture pattern for higher performing media? So you have, NVMe SSDs, SLC NAND, TLC NAND, QLC NAND. Now you have 3D crosspoint media. This media is a very high performing media. So if you were to do disaggregation, you do need to, worry about lots of other things, including low latency network. Your software stack has to be optimized and all that stuff. So that will be predominantly where you will see a lot of focus when we talk about disaggregated storage.
Okay. So next question is to Jay Menon. Reddy walked us through scalability, even performance, and functionality. But the immediate question that comes to mind is that, okay, it performs, but aren't we sort of introducing a whole bunch of security concerns with our data being physically separate from our servers, and now we have to manage multiple devices? So how what would you say about security concerns.
Yeah, thank you, Jay. Appreciate being here. I wouldn't call it security concerns. I think of them as security challenges because, they are clearly solvable. Now, security is a pretty complex topic, and I'm going to try and simplify security in one chart, and that's always hard to do. But let's think about in a multi-tenant cloud data center, what are we trying to protect ourselves against? Obviously, when you have multiple tenants, you want to be able to isolate your stuff from the stuff of other tenants, all of whom are sharing the network and potentially sharing the disaggregated storage that we just talked about. The other thing you also want to do as a tenant is you even want to isolate yourself from the actual service provider or the cloud provider. So really, there's really two sort of potential threats, if you will, from a security perspective. And when you're trying to isolate, what you're really trying to do is you want to isolate both the data and the access to that data. So those are two different things. So from a data perspective, you want to protect the data as it flows over the network by using things like encryption, and you want to protect it on the media by using encryption at rest. The challenge, of course, is how do you do this at high performance? And for that, I think additional hardware and or data-centric processors can help you do that. It's important to make sure that each tenant gets their own key, that stuff is pulled from a key management server and the keys are stored in secure enclaves. All of that kind of stuff is important to make this work. And then you have to worry about the access to the data. Now, data is accessed two different ways. You've got the data plane access, which is read and write my data for me. And you've also got the control plane, which is the way people come and say, hey, create me a new volume, delete a volume, do a snapshot, all of these kinds of things in a storage context. And so in both of those things, you do have to worry about how you protect those things, how do you authenticate with this new NVMe over Fabric kind of technology, which in my mind for disaggregated storage is really the only way to truly disaggregate. I think we heard about older technologies like iSCSI and so forth. I don't believe that they will do the job. I think NVMe over TCP, NVMe over Fabric, very critical to do that. And there are standards within NVMe over Fabric, like in-band authentication, that you want to make sure that people are not spoofing. And then you have to use TLS for the control plane and potentially for the data plane. And the last thing you need to do is, when you're handling resources to multiple tenants, you want to make sure you clean things up before you give it to the next guy. And this is really broadly true for no matter what resource, even though I talked a lot in the storage context. This is true if you're trying to disaggregate memory, like Amir talked about, or try to disaggregate GPUs. How do you clean up the state in the GPU before you give it to somebody else? It's sort of generic how you handle these things. So, it's not a concern. It's a challenge. It has to be done carefully. Many aspects to it, and clearly a little bit harder than if my storage was local.
Okay. Yeah, storage was a good context to talk about, because if you can solve security for storage, then presumably you can solve security for more stateless things like compute and GPUs. So that was a good context. But this kind of takes me to the most important question here, which is Jay's answer as well as the references made by Reddy talked about services at a large scale. And so services at a large scale across possibly the whole data center. And then previously we were talking about latency as well as bandwidth. So this is all leading to throwing the complexity all at the door of the network. So then the most important question is then to Parantap is then, can the data center networks keep up with all these features as well as bandwidth and latency?
Yeah, that's a great question, Jay, and thanks for the input, everyone. I think this is a great panelist set of panelists. The way I wanted to address the question was to just reduce it down to very simple things. What does the traffic need? What does the DAG traffic need from the data center network infrastructure? And it boils down to very simple things like lossless, high bandwidth, and low latency. Now, who provides the losslessness in lossless is an interesting topic. We'll get to that pretty quickly. But pretty much that's what they need. And if you look at the other traffic flows that uses the data center infrastructure, there are tons of other internet-based flows or other sync flows. But from DAG need point of view, those are the ones that are asked for. Now, if you unpack the lossless need, it comes down to let me put it this way. So if I had infinite bandwidth inside the data center, losslessness is not an issue because everybody is going to reach the other side and there is no congestion, nothing. But infinite bandwidth is not there. So because there are hotspots and then there are in-cast issues where everybody is trying to get to the same server. And then there's pockets of loss here and there that shows up. Now the question is, who is going to ensure it is lossless end to end? Now, we can go back to technologies like fiber channel or converged Ethernet, where it's a layer 2 technology which kind of works on credits, and they kind of ensure losslessness in those kind of technology, but they don't fit into hyperscale data centers or large-scale data center because they don't scale, and it is layer 2 in the very definition of it. Now, we can try to make the network devices buffer some traffic if it is going to get dropped. So why don't you buffer it and then when the congestion goes away and send it over? Those things also don't work because buffering adds latency that goes against the low latency requirement, and you can never guarantee zero loss. And what ends up happening is if you have a 12.8 terabits per second switch, in order to buffer for 1 millisecond, you need tremendous amount of memory, and these things cannot have that memory, right? So those things don't work. So what you come down to is the endpoints have to handle the losslessness. So essentially through retransmit. And if you go into the next slide, Jay, I do have another slide there. So if you go to the next slide, thank you. So what happens is essentially the endpoint can handle those through retransmit, and that doesn't have to happen all the time, but it happens when the transient packet drop shows up. And the low latency part is essentially broken down into two parts. So the latency on the fiber is really minimal. It's light speed. So the latency on the fiber is not there. The only latency is incurred by the buffering. And when you have shallow buffer, it is good because you drop the packet, you don't incur latency. So the way we build the data centers actually lines up well with the new technologies that are getting built. And if you go to the summary, you see that we kind of like the TCP algorithms on both sides, which takes care of the losslessness and the congestion control. And I wish that there are TCP technology that fits into in a way where the CPUs are not used too much.
Yeah, that's a good sort of summary of networking. I think it's a 2-minute tutorial to high performance data center networking. So thank you for that. So that was a 2-minute tutorial on high performance scalable data center networks. So let's go into a second round of discussions here and back to Amir, where we have, so I think Manoj mentioned it, resource stranding. And so today we use lots and lots of regular SKUs, and then basically those have their own local resources for CPU or memory or storage. And so can you talk about what resource stranding is and the scale of this resource stranding and any other sort of challenges that may come in this area?
Sure. I'll talk about the progression of how companies, again, get to where they are and why they start looking for things like disaggregation. When companies have a relatively small number of applications and they're building infrastructure to suit those, they tend to optimize the server SKU or the configuration of the SKU of the server for that particular application. So if you have a database, you may put fairly large CPUs and fast storage to allow it to serve that traffic. And that's really application optimized server design. Now, what happens is as these companies grow, inherently the number of applications they have, it may go from 10 key applications, where for each one of those 10 applications, it had its own unique server, to thousands of different applications. Now, when you have thousands of applications, there's no possible way you can manage 1,000 different types of server configurations. Some companies allow that number of servers to creep, and I've seen companies that have up to 60 different types of server configurations they deploy. At some point, someone in the supply chain says, that's it, enough, we can't do that, we need to simplify. And if you have technologies that allow you to disaggregate, if it's disaggregating drives, spinning drives, or flash, or if you have virtualization for CPU, then you can start building server SKUs that are really built around the commodities, around flash, CPUs, drives, maybe even in the future DRAM. And that makes things much easier on the supply chain. And it really allows you to have trade-offs. Now, the supply chain becomes easier. If you don't have any disaggregation technology, you're trading off utilization. And you're going to pick the server that most closely matches the particular application that's being run. None of them are going to be perfect at that point. And so I came across this in one of the companies I worked for in the past, where they decided that they could no longer manage 60 different types of servers, and they decided on a single server SKU, with a few exceptions here and there, but more or less the majority was one server type. And the numbers I have on the slide here is a representation of what utilization looked like, because they didn't have anything to disaggregate with. CPUs had around 4 to 5% utilization on average. Sure, some applications had 80% CPU utilization, but on average it was low. DRAM was around 10%. Flash and hard drives were around 3 to 4% of the capacity used was being utilized. And this is a company that would spend hundreds of millions, close to $1 billion on infrastructure, and you're only using less than 10% of that commodity that you're buying. And so it has a huge financial impact on the company. And what I like to see is technologies that are emerging that allow you to begin to disaggregate, because it allows you really to custom tailor the amount of commodity, if it's CPU, drives, flash, that you're allocating to these applications, and it allows you to get much higher levels of utilization at that point.
Yeah, that last point is so true. Indeed, we see a lot of SKU variation come from just trying to change, maybe for example, the SSD content in a server, and you'll see the similar SKU with 4 or 5 different SSD sizes. So that last point I think is key here. So let's move on to the next question. And for a moment, or for actually 2 minutes and 30 seconds, let's try to see if this data center disaggregation is a hyperscale thing only, or are there other computing segments that benefit from it? And for that, we will ask Manoj to share his thoughts.
Right. I thought about, I've been thinking about this question, and then let me answer it in a way perhaps I interpret it, and then we'll see if it addresses your question, Jay. One thing is basically disaggregation that I talked in the past, and everybody has really given a good context of the disaggregation. Whole point is really to reduce the stranding. So a hyperscale makes it much more visible because the scale is high. So anything that is stranded multiplied by a large number is a large amount of saving if I solve the problem. The question is basically, does that apply to everybody else? And I think the question comes down to really what exactly is a trade-off that happens here? Because anytime we want to change a model, for example, if I'm using local storage in my database versus if I'm going to do database that is going to run on the disaggregated storage, if it involves a change, it starts making sense at a particular volume or at a particular cost, that I'm trying so much that the saving starts making easy. There is a other side of this coin, is that means as the solutions become available, that actually makes that cost become much more acceptable, then it becomes easy. So I think the disaggregation is not going to be the hyperscale thing only because the scale is increasing in most of the segments. The amount of data that you're storing, amount of data that you're crunching, the applications that you're running that require the compute resources. So all these things are changing, and especially solutions available out there are going to drive that need for continue to scale out at compute and storage level And important thing is to make sure that the solution from the storage service keep appearing, which will address that need. So I think disaggregation does apply and will apply to hyperscale. And Amir had given a very good example of it's not a new thing. SAN was a disaggregation. Many of the things that have been there. The question has been is that now, as Parantab mentioned, the network has been able to enable that, and that is available to most of the use cases now. So most of the users should be able to take advantage of it and should not remain and will not remain hyperscale thing, in my opinion. The other aspect of the question that you asked, is it only related to other segments? I'm interpreting that, is it only storage thing or is it applicable to anything else? And I think if you think from building block perspective, we talked about compute storage, but from service perspective also that happens and is happening more and more. Taking Facebook example, of course, database was the bottleneck at a point of time. That's why the Memcached was built as a caching layer in front of it. So most of the caching that could have happened inside the database server, that became the front end layer, which basically got completely separated from the database as a caching layer. So you can think of that as basically applications which are accessing the database now are using this disaggregated service, which is a caching service, and behind that with database server. So I think services do this for some time also, and will continue to become more and more. And potentially in the future building blocks, I think in general, anything that has a potential for stranded capacity, I think, I forgot exactly, I think maybe Jay or Reddy or somebody mentioned GPUs or next generation memories and NAND technologies that are coming across that Reddy mentioned about. These are high performance components, high value components. So if at some point of time, you may see that actually those can create the same problem that is clearly shown in the flash and a compute today. Anything that grows that has the potential of stranding because of other resources in the block, I think has a potential for building. And one more tiny point I would like to make is that when we say disaggregation, the scale of that disaggregation can vary. Some of those could be going across the regions. You can think of a backup and DR becoming a disaggregated service, or even the storage becoming across the network as a disaggregation range of the domains. And disaggregation could be within a system or multiple small subsystems which are connected with a very extremely high performance network that allows to share very high performance network. So I think disaggregation is not new, and I don't think it's going to be targeted only for hyperscale, and not only it will be targeted only for storage. I think it has potential and opportunity to go across multiple technologies and use cases.
I see. So like other technologies in this whole cloud stream, so hyperscale will lead and other people will adopt whatever we come up with some modifications then.
Yes, and I think I'm also hoping that it will work other way around also.
Sure. That we learn from the past.
Yes, so HPC has shown how to disaggregate also, so we definitely leverage all of that. Yeah.
Yes, sometimes we have to get our heads out of our own sand.
Yes, absolutely.
Okay, so so far, so far we've been. This next question is for Reddy. So why is this feasible now? Why weren't we doing this 3 years ago or 4 years ago, when some of these challenges were as big? And then the other part of this question is, will it continue to work? Will this disaggregation thing continue to work with newer memories and newer storage technologies coming down the pipe? And since you're at Intel, you probably have a sort of very good perspective into this.
Yeah, so thanks, Jay. So now, as we talked, disaggregation is not something new, right? So we essentially focused quite a bit on the fact that disaggregation has been there for quite some time. As you can see that the infrastructure aspect of it, the networking, we talked about the networking, the software, some of the software innovations like distributed scale out, and then the solution maturity. So the solution in the sense, it's one thing to say I have the storage software stack, but you need to be able to, get the end-to-end solution working. So how do you deploy that in a container? How do you consume? How do you assign a specific virtual block volume to a virtual machine? So the whole aspect of the solution that plus the underlying, underpinning of the infrastructure components, plus the software maturity has been there for quite some time. But if you look at, most of the use cases out there, they're mostly relegated to, the workloads that actually can tolerate reasonable amount of latency, sometimes in the order of milliseconds. Now, the challenge is going to be going forward. We have been doing quite a bit of work in this space with fabrics, NVMe over fabrics, NVMe being the fundamental, the building block protocol, both on the initiator side as well as on the target side. The challenge is going to be, how do you take the innovations on the networking side, specifically on the fabrics-based, networking technologies, and then take the emerging, highly optimized NVMe and NVMe over fabrics protocols, and deploy that on the low latency, network to deliver, for the workloads that really require low latency. Now, why do you need low latency? If you look at the emerging media, for example, storage class memory as one example, 3D crosspoint Optane SSDs, they actually give you, depending on the media type, anywhere between hundreds of nanoseconds to single-digit microsecond type of latency. Now, if you actually take that media, which is expensive, and try to actually use it in every server, it becomes extremely premium commodity, right? So you should be able to, take advantage of some of the emerging innovations in the networking space, as well as, some of the software innovations out there to be able to say, how can I actually disaggregate, deliver low latency type of, performance requirements for emerging use cases. So that's where you will see a lot of traction, a lot of focus going forward. It doesn't mean it hasn't started yet. So you can see lots of deployments out there with NVMe or TCP/IP, some simple instantiations with a single target, single initiator kind of implementations out there. But in general, the focus is going to be, how do you deploy this at scale, right? So that's a second element. The third one is extreme disaggregation, in the sense, like Amir talked about it. Manoj actually mentioned this quite, in his previous talk as well. Is there are emerging technologies, emerging standards that are actually out there. So how do you do? So today you talk about disaggregation at a storage level. You talk about disaggregation using accelerators. Now, can you disaggregate the compute? Can you disaggregate the storage? Can you disaggregate memory? If you look at the emerging standards, for example, Compute Express Link, it actually gives you a lot more richer, fine-grained constructs. You can actually have a accelerator that can actually sit in the cache hierarchy, for example. You can have an accelerator that can actually sit in the memory hierarchy. So you could actually take the existing standards-based innovations that are actually happening, which will open up the doors quite a bit in terms of doing extreme disaggregation. You can actually do pooling in a rack using CXL accelerators that are premium in nature, that you want to be able to share resources within the rack, maybe among racks, for example. So if you look at the future, that's probably where you will see a lot of traction in the industry on what is the best way to disaggregate some of the premium devices out there with the standards that can actually evolve and support that type of architecture.
Thanks, Reddy. So Reddy mentioned some extremely high performance media, and also the advantages of using a precious resource like that in a shared manner. But then that leads to the question of, are we stuck with low-level protocols such as block storage or NVMe or TCP for this kind of disaggregation, or can we get high performance for object or file abstractions, because those definitely scale much better across a whole data center? And so we'll address this question to Jay Menon because of his GPFS background. Jay, would you like to take us through this particular thought?
Yeah, thanks, Jay. Appreciate it. Yeah, so in my opinion, I think that disaggregating storage at the block level has been the harder problem. I don't think we've had a good solution for a very long time. I think, as I mentioned before, we've had iSCSI and Fiber Channel and so forth, but I think truly useful disaggregation and scale-out block storage is happening, and all of the panelists have talked about, what are all the reasons why that's true. I think it's actually easier to do disaggregation for object and file storage. And in fact, we've had useful systems there for a longer period of time. GPFS, I don't want to age myself, so I won't tell you how old it is, but it's been around for, for a long time. You know, let me just start by just maybe pointing out a few key principles that that I think we should that people should follow when we think about high performance file or object storage. You know, the first one I would argue is that if you want focus on the one thing you want to be very high performance at. I think every time people have built a good file storage that's high performance, and then they put an S3 gateway on top, well, the object stuff is not very good, or vice versa. You start with an object storage that's very good, then put a NAS gateway on top of it to get a filer, and that, then the file stuff is not very good. So if you really want high performance, my own thinking is that you really need to focus on that. And then we really have to follow all the things that we've been talking about today. I mean, 100 gig networks are here, going to 400 gigs. SSDs, going to, let's say Optane or 3D Crosspoint. We had a really nice 2-minute treatise on like what is really important in networking, we talked about end-to-end congestion control, solving the incast problem, but I think really good low tail latency is also very, very important. I'm not sure we talked about that very much today. What we call data-centric computing is also important, because as you go to 100 gig and 400 gig and you want to do encryption end-to-end and you want to do compression end-to-end, you've got to have some different kinds of computing to make that efficient. So those are all key principles. If you want to get high performance, you got to do some of those things. Now let's talk about file and object separately. File storage, I think we've had them. I mean, these are not new. We've had them for a while. And, there are really, really scale out, extremely high performance file systems that scale to thousands of file servers today. They give you terabytes per second of bandwidth. So really high performance stuff. Typically, the high performance file systems typically have their own special client on the compute side and not go through sort of NFS. That's how the highest performing file systems are today. And the last thing I'll mention, it's kind of interesting, we've been poking at this for a while. Typically, these file servers, which scale independent of the compute servers, use local storage, use direct attached storage. But interestingly now, with these new technologies of NVMe over Fabric, NVMe over TCP, etc., we're finding interesting cases where you can actually disaggregate even below the file system layer to a set of block storage devices that are also scale out. So you can almost think of, kind of 3 layers. You got the compute server scaling out, you got the file server scaling out, and then you got the block servers below it scaling out. And you'd think it's not as good as DAS, but it turns out with these new technologies, and because you're eliminating some file server to file server traffic by having everything shared underneath all of these file servers, there are interesting advantages, including obviously, less stranding, as people called it today, and better utilization of the storage. So that's sort of the file storage summary. The object storage, and I'm mostly focusing here on the S3 kind of API, which has become the de facto standard for object storage. Sometimes I notice people will talk about key value store as a much simpler form of object storage, where the metadata is basically nothing but the key. But let me just focus on the S3 style of object storage. And in the past, it's typically been used for low performance archival use cases, typically focused on spinning disk, when you're storing that kind of data where performance is not important, why use flash? But really recently, there has been a lot of surge and interest in scale out, high performance, disaggregated object stores that use flash and so forth. They're still not up to the kind of terabytes per second bandwidth that file will give you. Most of the numbers I've seen are gigabytes per second, not terabytes per second. So there's an interesting dynamic that's emerging here as the high performance object stores come into play. Will they replace files? Will they become the most interesting kind of storage for the new generation and next generation applications like AI and ML. So that's a really interesting topic. So, my summary is, yes, you can absolutely get very high performance, very scale out object and file storage. Files are ahead today, but watch this space.
Okay, that's a good summary of large scale storage services. So we have, I think, time for one more question, and we'll direct it to Parantap. And this is, so some of the things that we had been talking about in AI ML, for example, people talk about, hey, let's use RDMA, right? And even for storage, sometimes people do that. And my question to Parantap is that, like everything else, are we just throwing the problem at
Jay? Yeah, thanks for the question. So I would go back to my last answer also while answering this question. So how RDMA came into picture, and more of RDMA over Converged Ethernet, the Rocky kind of protocols came into picture, was essentially looking for a fiber channel related L2 network to start with, and because RDMA was based on that, and then in RDMA, the Rocky version 1, it basically was trying to use Ethernet and all the frame space inside Ethernet to have some kind of a lossless behavior. And in a hyperscale environment, those things don't work. Simply doesn't work because the L2 domain is inside under a rack. So once the packet leaves the L2 domain, that is the top of rack, it becomes an IP packet. So whatever you put into the Ethernet frame is lost. It's shredded pretty much. Now, in the Rocky version 2, where the same information got put into a UDP packet inside the IP header, it becomes a little more friendly for the IP network infrastructure. But if you look at the specification, they look for ECN kind of notification back from the IP network in case of congestion as an early indicator of congestion setting in so that they can buffer on the server. And if you look at a regular hyperscale network, which has to live with the legacy network, it's a brownfield network, not a greenfield network, turning on those ECNs are pretty complex also. And in many cases, the ECN work with the RAID profile that works with the TCP, because RAID is connected with the TCP profiles, and the Rocky V2 stuff is UDP. So there are some things where the network guys cannot really fix some of those problems because it is kind of tied with the platform that they have. Now, there is a lossy part of Rocky V2 where the higher layer protocol stack can retransmit some of the packets if it hasn't reached the other end. So which takes care of the congestion control, not the congestion control, the losslessness part of it, because it retransmits the packet if it hasn't reached the other side. But the concerns would be that if the network behavior changes, like suddenly there are some congestion that shows up, the performance expectation from those kind of protocols can vary widely. And so there would be those concerns. And the congestion control part, which comes naturally with TCP, is not there in those kind of lossy higher layer protocol because it is being handled from a higher layer. So those would be my concerns, but I would say that Rocky V2 can work on an IP network, but I would rather have something to do with TCP on both sides, which handles losslessness as well as the congestion control part.
With TCP, in short?
Yeah, I like it. But TCP has, like, if you have TCP in the kernel, then it's not optimized. It's kind of age-old. So if you look at the SPTK part and use the other threads, it eases up. Yeah. Okay.
So that's a good note to end the session on. This was very informational and also very thought-provoking. So panelists, thank you very much. And this is an interesting topic, and it will continue to evolve. But I think we've gotten a fairly good set of thinking points in the last 35 minutes or so. So thank you.
Hey guys, this is Amir Michael. We'll take some of the Q&A questions that we got during the session right now.
Sorry, I was
go live from there. All right, we got Jay to go ahead and lead the Q&A.
Right, sorry, my phone was on mute. Sorry, guys, rookie mistake. So the first question we have is on blast radius. Jay, given some of your work, can you comment on blast radius increasing when you do disaggregation?
Yes, can you hear me fine?
Yes.
Thanks for the question. Yes, so I think that you do have to pay greater attention to blast radius. If things break, then potentially more servers are affected as a result of that. And I think that the right way to address that is you do have to have higher levels of availability constructs. Typically in these kind of environments, especially in hyperscaler environments, people use very wide levels of erasure coding, all the way from 10+3 failure to 20+4 to 32+8, so that you can have very large numbers of failures and very fast rebuilds without impacting the servers. I think it's also important to support different levels of availability for different tenants. I mean, I think of these, especially in a hyperscaler environment, you have to have the ability to support different tenants at their availability levels. And so, there could be people where losing data is not important because, maybe it's a CDN cache and you've got the data stored somewhere else and it's okay. And all the way to, 10, 11, 12 durability levels. And so I think it is also important in these kind of disaggregated storage settings to be able to support multiple levels on a per tenant basis of the kind of availability you want to support. So yes, it is blast radius is something we absolutely think about a lot, and it has to be handled carefully. I think that's the way I think about it. Back to you, Jay.
So that's good. There was a question also embedded in it in terms of silos, that infrastructure currently is in silos and wouldn't we be breaking silos? Manoj, your thoughts on that?
Sure. I think that exactly is the right point for the disaggregation, that once we create the storage, and you have to look at the storage as a reliable service available, which do make sure that, as Jay pointed about, the blast radius has to be handled with more reliable storage as a storage service. Once you do that, actually the silos do go down. Today you have siloed capacity when you have local storage or the use-based storage service, that storage that you have within the hardware. So by disaggregating, you're making sure that that storage can be shared across multiple services, multiple applications. And so the silos can be broken down. You combine all the storage, disaggregate it together, make sure it is available, and that way you can reduce the blast radius. So there has to be a careful consideration for making sure that we have the storage available, blast radius is contained on that one, and that way the infrastructure silos will go down with the disaggregation. And this is what is happening in many hyperscalers as we see.
Okay.
Back to you, Jay.
Thank you, Manoj. Yeah, thank you, Manoj. Amit, the next question is to you. And since you started talking about SANs first, so the question is, isn't data center network and storage already mostly disaggregated? And I think hyperscale sort of biased to your answer, please.
Sure. Yeah, that's a good question. When I think about the network, I think that's a resource that ties everything together. So by nature, it is disaggregated. So I would agree with that statement. And because of that, people don't normally think about disaggregating the network. When it comes to storage, there's different types of storage. There's high latency, low bandwidth storage, things that you might associate with disks. Those are largely disaggregated. That's a correct statement. There's things like commercial products you can buy, like SANs, to do that. There's open source projects like Ceph, like HDFS, Hadoop, all those things, you can do that and disaggregate your slower storage. When it comes to high speed, high throughput, low latency storage, that is something that is still not as well established in the industry. And adoption is slowly happening. As far as I know, there's a number of commercial solutions for that. And then open source, there are drivers that can help get you part of the way there today. NVMe over TCP drivers, for example. Anything faster than that, if we're talking about much higher speed storage, that's typically on the host like RAM, for example. I'm not aware of anything that's happening there just because of the nature of and the sensitivity to latencies. It's hard to do that over network today. Back to you, Jay.
Hey, Jay, can I add to that to answer?
Go for it.
Yeah, so I think, I think just accentuating what Amir said, the way I see all disaggregation happening, this is sort of, I don't see disaggregation as, as sort of an exact point in time. I think it's a journey from 0 to 100. When you start, you don't have good performance when you disaggregate, and you don't have good scale when you disaggregate. And often you start with a network that is uniquely purposed for that thing that you're trying to disaggregate. For example, you start with fiber channel for storage. And performance, and the way to define performance is how good is it compared to keeping the thing local. I think that's the ultimate comparison point. And so, your goal with disaggregation should be that it is so good that you don't have to have the service local anymore, right? That is the ultimate goal. That would be the 100. You start with 1 and you get to 100. So you're trying to improve performance, you're trying to improve scale, and I think ultimately, many of us believe that you want to make all of this stuff work with IP over Ethernet as opposed to something that is not. And so I think all of these things are on a journey. I think the ultimate test of whether things are good enough is you go take a look at Amazon, and they have EBS, which is disaggregated storage, and they also have local instant storage. And I think ultimately, an instant storage is actually growing relative to EBS. And if disaggregated storage were good enough, that would, you'd see a shrinking of local storage and a growth in the other direction. So I think yes, storage is disaggregated, but it's not clear to me it's good enough. And I think all things will be on this journey. I think Amir talked about memory, and I think we'll see the same thing happening. We will see, networks that are focused on making memory disaggregated, whether it's Gen Z or CXL or other things. Performance will not be quite as good. Scale won't be quite as good. And when I say scale, I mean it has to work, in a hyperscaler environment at 1,000 racks. So I think there's 3 dimensions of get the performance where you need it, get the scale where you need it, and ultimately, if you can make it work on IP over Ethernet, I think that's where you really want to get to. So it's a journey. Journey has begun, but I don't think we're there at the end. Back to you, Jay.
Thanks, Jay. I think Parantab gets the hardest questions on this panel. So here's one more. So there's a question on when do you think hyperscalers deploy composable disaggregated solutions? And Parantab, since you manage not just network, but also all infrastructure, can you take a wild guess at that? Hello? Hello, Manoj, does anybody else want to?
Sure. Yeah, sure, I can do that, unless Parantab comes back. Hey, I do think actually that the hyperscaler are already deploying the disaggregated storage, and I think Jay mentioned before some of the other solutions, but that's happening in many hyperscalers already. The key difference remains actually the solutions that are very latency sensitive and have that kind of performance requirements continue to be on the local storage, but many of them which can be moved to the batch kind of queries, etc. The disaggregation has been happening for some time, and I think it will continue to grow more and more as we see.
Okay.
Yeah, and I
think. Go ahead.
No, I was also going to add that I think, I think the next step, which I think the questioner was asking about, is following disaggregation. I think the next step to that is the composability aspect of it, right? Because you do want to finally compose things back. whether you compose them at a server level or you compose them at a data center level. And in my mind, the more to the right you are, the better. I think those things are happening because ultimately, Amir talked about it. I think Manoj talked about it, the server skew reduction and so forth. I think those things, for that to really work, you need disaggregation at high performance, you need disaggregation at high scale, and then you need to be able to bring the composability back so that, as far as the user is concerned, they don't really know the difference between whether the server that they're running on is actually a composed server with resources that are distributed across the network. And I think that's where we're headed, in my opinion.
Yeah. So with that, we have run out of time. Technically, we are a minute over. We had a couple of questions from the audience still left. We would need to get in touch with you offline, but I think we have to wrap up this panel discussion now. With that, thank you, audience. Thank you for the questions. Thank you for listening, and thank you for attending, and thank you, panelists.